We're on the cusp of a revolution in medicine, and its engine is artificial intelligence. For decades, biomedical research has followed a familiar path. A scientist has a hypothesis, runs experiments, analyzes the results, and maybe, just maybe, makes a breakthrough. This process is slow, expensive, and often hits dead ends. But what if we could change the entire game? This isn't about using AI as just another lab tool. It's about fundamentally redesigning how we discover and develop new treatments. It's about shifting from a slow, linear process to a dynamic, supercharged workflow that can tackle the incredible complexity of human disease. This is the strategic imperative for every organization that wants to lead in the new era of medicine. So how do we do it? We can build our strategy on 3 core pillars. First, AI-augmented discovery. Forget spending months manually sifting through scientific papers. AI can read millions of documents, analyze clinical trial data, and scan genetic databases in minutes. It connects the dots in ways no human could, uncovering non-obvious links between genes and diseases, identifying brand new drug targets, and generating hypotheses we hadn't even thought to ask. We're moving from testing a handful of ideas to exploring a universe of data-driven possibilities. The second pillar is AI-driven experimentation. The lab is where great ideas often meet a slow, painful reality. It's a major bottleneck, but AI can change that. Imagine an AI that designs the perfect molecule to hit a specific disease target, predicts its properties before it's even synthesized, and then maps out the most efficient way to test it in the lab. It can navigate the complex decision trees of experimental design, drastically cutting down on the costly and time-consuming trial and error that defines so much of R&D. This accelerates the cycle of design, test, and learn from months to weeks, or even days. Our third pillar is AI for data synthesis. Modern biology is drowning in data genomics, proteomics, imaging. Clinical Notes sits a tidal wave of information from different sources in different formats. AI is uniquely brilliant at weaving all of this together. It can integrate these disparate datasets to find hidden biological signatures that predict how a patient will respond to a drug, or create comprehensive models of how a disease actually works. It turns this data overload from a massive headache into our most powerful strategic asset. To make these pillars a reality, we need an operational model, a playbook for success. We call it the play, a 4-phase, continuous cycle. It starts with data curation and problem framing. You have to get the first step right. This means gathering high-quality data and defining the scientific question in a way an AI can understand. Next is model selection and prompt design. Here, you choose the right AI tool for the job, be it a large language model or something else, and give it crystal clear instructions. Think of it as writing the perfect question to get the perfect answer. The third phase is execution and critical evaluation. We run the AI, but we don't blindly trust it. We have to be rigorous skeptics. Every output, every insight must be challenged and validated against established biological knowledge and real-world experiments. The final phase is iterative refinement. We take what we've learned and we loop back. We refine our data, tweak our AI models, and sharpen our questions. It's a closed-loop system that gets smarter and more effective with every single cycle. Of course, this journey isn't without its challenges. AI is only as good as the data it's trained on. Biased or messy data leads to garbage results. We also have the black box problem. Sometimes we don't know how the AI reached its conclusion, which is a major hurdle for scientific trust. And we must be vigilant against hallucinations, where AI confidently presents false information. The solution is robust data governance, a non-negotiable focus on explainable AI, and a rule that no AI insight is considered fact until it's proven in the lab. Finally, we need to bridge the cultural gap between lab scientists and data scientists, creating integrated teams that speak the same language. To move forward, the path is clear. We must invest in our data infrastructure, build cross-functional teams, and start with small, high-impact pilot projects to prove the value and refine our playbook. The integration of AI isn't just about new software. It's a paradigm shift in how we approach science itself. By embracing this structured, critical, and iterative framework, we can dramatically shorten the timeline from discovery to cure and unlock a new frontier of medicine. Thank you for watching. If you found this valuable, please like, subscribe, and join us on this incredible journey.